Imagine a world where every snapshot contributes to conservation. With image recognition technology, we're turning this vision into reality, enabling us to identify endangered species in the blink of an eye. Notably, birds are excellent indicators of an ecosystem's health. Birds are responsible for linking multiple ecosystems together, are sensitive to changes in their environment, and are easy to observe. Thus, the population trends of birds often reflect the quality of their habitat and the overall health of an ecosystem. However, almost half of all bird species today are in decline. We decided to take a local approach to biodiversity conservation to support our communities. Our study's objective was to develop and contrast two AI models that could recognize endangered bird species in Ontario. The first model employed transfer learning with ResNet 18, and the second model was a custom convolutional neural network model. As seen on the left, certain groups of bird species are facing declining populations more rapidly than others. We selected four bird species listed as endangered on the Species at Risk in Ontario list as our target species: the piping plover, loggerhead shrike, Acadian flycatcher, and the barn owl, as seen on the right.
For the rest of this presentation, we will refer to the convolutional neural network as CNN. A neural network is a method in artificial intelligence that teaches computers to process data similar to a human brain. Thus, they are made up of layers of neurons. Pixels are fed through each neuron layer, where it will be connected to the next layer through channels. Each channel is associated with a weight, and each neuron is associated with a bias. A function is used to determine whether the particular neuron will continue to get passed on to the next layer. This process is repeated iteratively over epochs. An epoch is a round of training where all of the training data has been fed through the model. During epochs, the predicted output is compared against the correct label to calculate the magnitude of error and passed back into the network. Based on this information, the weights and biases are adjusted. We sourced 2,615 images of each target species from the open source platform eBird. Another 2,615 bird images were sourced from Kaggle to form the other category. This dataset composed of 523 different species with 5 images per species. Then the labels 0, 1, 2, 3, and 4 were assigned to the categories of barn owl, piping plover, loggerhead shrike, Acadian flycatcher, and other, respectively. Before training the model with the data, each image went through pre-processing to increase the diversity of our dataset, exposing the model to a wider range of possible real-world scenarios. These transformations included rescaling, rotation, flipping, and more. For the CNN, the images were resized to 224 by 224. After this, all images were put through image data generator function, which performed the various transformations. The CNN we built consisted of 3 convolutional layers, with increasing filters 32, 64, and 128. Following each layer, batch normalization was applied to reduce overfitting. Each convolutional layer is composed of a ReLU-activated 3x3 kernel convolution layer and a 2x2 max pooling layer to reduce image size. The fully connected layer of this model flattened data and was fed through a 512 neuron dense layer equipped with a ReLU activation function. This introduced nonlinearity to the model. This nonlinearity allows the network to learn more complex relationships between the features. The FC connects information extracted from the previous steps to the output. The image would then go through one final dense layer with 5 neurons activated on softmax. This is used to convert raw scores into probabilities. Here is a sample result of what an image would look like after the first convolution. It highlights what the model perceives as important features for classification. Some filters activate strongly to edges or color transformations, while others respond to particular shapes and textures. This study employed the ResNet 18 model, which is a pre-trained model with 18 layers, trained extensively on large databases such as ImageNet, which contains over 14 million images. ResNet is unique because it has residual connections, which allows data that's being fed into the current layer to be also fed into later layers, therefore getting combined with transferred inputs and allowing for a more complex and flexible model. For this study, we froze the first 17 of 18 layers and only changed the last layer, which allowed the model to retain its previously learned patterns. The last layer was replaced by a new linear layer using the ReLU function. After a dropout layer was added, which combats overfitting by randomly dropping a fraction of neurons during training. Finally, there is a linear layer which contains 5 neurons for the 5 classes. Here is a sample result of what the first convolutional filters looked like and what an image looked after a convolution. The visualizations appear abstract as the first layer in a deep neural network often learns very basic and generic features. The presence of color suggests that the network may have been learning to recognize patterns based on color gradients and variations.
We'll start off with the results for transfer learning. As seen in the graph on the left, the validation accuracy of our transfer learning model reached around 93.1%, which is quite epic considering the limitations. The loss graph on the right measures how wrong the model's predictions are. If the model's predictions are perfect, the loss is 0. Otherwise, the loss is greater. An accuracy drop and loss increase in epoch 4 of this model suggests overfitting, where the model fits exactly against the training data and generalizes poorly to new, unseen data. Precision measures the proportion of true predictions to all predictions, and recall measures the proportion of true identified instances out of all actual instances. F1 score is the harmonic mean of precision and recall. It provides a balanced measure of the model's performance. For each metric, the higher the score, the better. Looking at both graphs, there's an overall increase in metrics. These properties indicate the model is correctly classifying more instances over time, demonstrating improved reliability over epochs. Turning to our custom-built CNN model, the model also generally increased in accuracy over epochs, and the model loss declined. As seen in the graph, the final train accuracy reached around 97.4%, while the final validation accuracy was only around 85.7%. A similar gap in train and validation loss could be seen. This discrepancy between the training and validation metrics, especially accuracy, highlights a potential gap in the model's ability to generalize to new, unseen data. This signifies that the CNN model was more prone to overfitting than the transfer learning model. Though the CNN model performed slightly worse compared to the transfer learning model, it was self-defined to suit our specific needs, and it offered us greater control over the architecture, allowing for more tailored optimizations and adjustments. To compare the results of both models, a confusion matrix was plotted for each, using their validation data. As seen by the pronounced diagonal, both confusion matrices demonstrate fairly accurate models that correctly classify species. It can be seen that the CNN model struggled with accurately identifying the non-target species. However, this was expected as the dataset was very diverse, making it difficult for the model to identify a consistent pattern within the limited data of the other species. So the difference in performance between the two models stem from their complexity, training time, and accuracy. Using the same data, the transfer learning model completed 5 epochs of training in around 20 minutes, while the CNN took over 90 minutes. The 3-layer CNN lacks a head start of the pre-trained model, requiring more time and resources to learn features. Hence, while both models show capacity to learn and improve over epochs, the depth and pre-trained features of the ResNet 18 model in transfer learning offers a distinct advantage in terms of speed and efficiency, ultimately leading to a higher accuracy with a better overall performance under the same conditions.
The integration of AI into conservation strategies represents a transformative leap forward in our efforts to conserve biodiversity in the face of environmental challenges. By automating species recognition from images, conservationists may be able to easily track population changes within a habitat and create protective measures based on data driven decisions. AI's ability to bypass the need for tedious human labor and its capacity to process vast quantities of data very quickly and accurately allows for more effective species conservation. Looking forward, we emphasize the importance of expanding datasets to include a more diverse array of species.